I decided it's worth doing this test in a separate video because that last video was getting a little long. I went out on the internet, and on this wikimedia.org I found this diagram, and from what I can tell, Wikimedia is a freely usable website, so all credit to them for this diagram. But if you've taken a trigonometry course, you've most likely seen this circle before, where they give you the angles in radians here. We have pi over 6, pi over 4, pi over 3, pi over 2. All right, those are radians, and a full pi radian of measurement would take us all the way to half of the circle, whereas this is 2 pi. Hopefully that's old hat by now. And then we have the degree measurements here, 0, 30, 45, 60. I can't stand degrees. They drive me nuts. Pi is just so much more elegant once you get used to it. Now looking at the coordinates here, these dots here, if I go pi over 6 radians, that's the same as rotating through pi over 6 radians, and the coordinate here is root 3 over 2, 1/2. That's the Cartesian coordinate of this dot here, but we can actually treat these as vectors instead. I can say here is a vector, it's pointing right there, and its components, its ith and jth component, or x and y component, would be root 3 over 2, 1 over 2, and then I can do another vector right here. I'll just draw this vector like so, and its coordinates will be 1/2 and root 3 over 2. And both of these vectors, their length is 1. The reason I can tell is if we started a vector out here, pointing at this point here, this point is 1, 0. So its length is 1. All we're doing is rotating here. Well, what's the angle of measurement between these two vectors? If I swept out the theta here, how far is it not degree-wise, radians-wise? What kind of angle did I sweep from this blue vector to the red vector? Hopefully it's not too hard. We're at pi over 6 right here, and then up here, let me get a little bit thinner here. Up here we have pi over 3. To get a common denominator, 3 and 6, I can just multiply this by 2, so that will give me 2 pi over 6, which means I've swept out pi over 6 radians from the blue vector to the red vector. Since they're both normalized, doing the dot product between them should give me the same as saying the cosine of pi over 6. All right, let me actually write that out a little more explicit right here. Remember, let's say our red vector is A. This is vector A, and the blue vector is vector B, like so. If I say, I know I've shown this in previous videos, I hope this helps. The vector A dot that with the vector B gives us the magnitude of A. All right, but the magnitude of A is 1, so I don't necessarily need to write that, times the magnitude of B. Okay, but that's 1 as well, so there's no point in writing 1 times 1 times the cosine of the angle between them. Well, what's this angle here? It's pi over 6. So we can do a simple unit test by making vectors out of these coordinates here, doing the dot product, and that should give us the same as calling the cosine function with pi over 6. Now, you can see I kind of got started here before the video. I'm gonna put this up, drag this over here so you can still see the unit circle behind it. And the coordinates need to be, let's see, which one's A? The red one's A, so well, I guess it really doesn't matter. We'll say 1 over 2, or I could just say 0.5 f. That's the same as 1/2. And then I'm going to say square root of 3 divided by 2. So that is our first vector, or our vector A. Maybe it would help to just say A there. So 1/2 and root 3 over 2, and then vector 3D B. What's B's coordinates? It's square root of 3 over 2, square root 3.0 f divided by 2.0 f. Let me put my 0.0 f here as well. And then the second coordinate is again 0.5. So hopefully you can see the math here is actually internally for the dot product, the math is going to work out quite elegantly. Now you could have said, Jamie, you could have saved this in a temporary variable, but yeah, it's a unit test. It's 1, 2 square roots. Let's just move on. So float dot result gets A dot with B, and then expect float equal the dot result should be equal to the cosine of, I believe we defined pi, if I remember right, Control Alt L. Where did we define pi? I think we defined, oh, constants h. I think we put it in there. So let's do pound include. Let's try to be keep these things in alphabetical order. Math constants, and I believe let's right click here, open the document. Oh, pi is the only thing we put in there. Whatever. I'm not going to put a using up at the top though for math.pi because pi is I don't want to clash name-wise with anything else that might be included. So I'm actually going to just say math.pi and be explicit here, and it's pi divided by 6.0 f. So those two should be equal. Here's hoping. Let's build, see what we get. Build started. Build succeeded. I'm hoping for green here, and it looks like we got green. Lots of green. I'm feeling good. The dot product of two normalized vectors will be equal to the angle between them. In this case, we set it up for math.pi divided by 6. Pi over 6 radians is what we swept out there. So, okay, finally, I'm feeling a little bit better about these tests. If I really wanted to, I could make random float generator and randomize these every single time, but then it's hard to track random tests. If I did do that, I'd have to, in a case where the test failed, I'd have to save away which random case failed, which is an option. That would totally beat up my code a lot better than what I have now. But this is definitely pretty good and definitely better than nothing. So onwards and upwards, let's use vectors to do something else.